So here's another modified Atwood machine problem. They say that we hit this block M, capital M, to the right, so that right at the beginning of the problem, this says, I know it's a little blown up and granulated here, but x equals 0, so that's sort of where it starts, and it's going to move, and that's going to happen at what they say is t0, so at time 0, and the block's front of it's going to move up just till it gets to x equals d, and it's going to stop there, and that's going to happen at t1, and then it's going to start to move back again once it's slowed down in reverse directions, and the front of this block is going to get back to x equals 0 at time they're calling t2. They do mention in the description that it is a rough surface, so that means that we are going to have friction on the block there as it moves. So they ask us for two different free body diagrams here for the two different time frames. First, let's do a free body diagram as it moves from here to here, so it moves to the right, as they've got drawn in this picture here. So in that free body diagram, we are going to have gravity downwards here, of course. Now, they give us absolutely no indication of how long to draw it or whatever. We don't really know. So I'm just going to draw it the full length there, just so it's easy to see. Then you're going to have the normal force back up the other way. However big you drew gravity, that's how big you have to draw the normal force, because there's no acceleration in the y, so there's no net force in the y. So those two equal each other there. We have got, as it moves to the right, if there's a rough surface, then friction's going to be back to the left, and they give us no indication again of how exactly to calculate it. I'm just going to draw it 3 squares back, and I'm going to call that the force of friction there. And then finally, we've got that string pulling on the block there, so we are going to have a tension back. And again, don't know how big to draw it here. I'm just going to draw it 3 back, so there is a tension back there as well. So that's all the way up to the point that it stops. It's traveling to the right the entire time that this free body diagram applies. Eventually, this block's going to stop right here, and it's actually going to start to zoom this way to the left there. And that's when the second free body diagram comes into play. So on this one here, now we're moving to the left. So once again, we should have gravity down, same as before. So to counteract that and balance out the forces in the y direction, the normal is up, same as before. The force of friction now is going to be opposed to motion just like before, and it will be back the other way there. So there is the force of friction, and now we are going to have the tension that's pulling it to the left here. So the tension is going to go off in this direction here. So now I'll get to in a moment why the tensions do not necessarily have to be the same, but the frictions do have to be the same. That is definitely true. And how do we know that? Because the force of friction is the coefficient of friction times the normal force. And the normal force isn't going to change because that's going to just be equal and opposite to gravity in each case, and the mu is going to be the same in each case, so the force of friction has to be the same. So then generally speaking here, they then say, well, is the magnitude of the block's acceleration greater before the block reaches x equals d, so the first half of the trip up, or after? Explain your reasoning in terms of the forces you drew in the diagrams. So if you look here, our acceleration is actually going to be greater in this case. And why is it going to be greater in this case? Because these two forces are pointing in the same direction, so they're going to add up together to be a bigger net force together. Over here, the two forces are competing, so they're going to cancel each other out somewhat, and so you're going to have a smaller net force in this case, and that's going to lead to a smaller acceleration. And that's what you would basically write out on your description there. Over here, they want us to do a graph of velocity versus time. And so they want us to indicate the values of v0, t1, and t2 on the axes And make sure your graph is sketched to show that the block travels the same distance forward and backwards. So they're actually giving you a clue here. So to show same distance forward and backwards. Well, how's that going to show up on your graph? Since this is a velocity versus time graph, distance, or better said, displacement, is going to be equal to the area under the line. So they're sort of giving you a hint there about how you should draw your areas. This bold line here should obviously be 0 meters per second. I'm going to just pick this top gray line here to be V0, and that's our initial velocity. So we are going to slow down. We should have a constant acceleration, and that will give us a straight line graph on here. So what does that look like? Well, we're going to start at V0, and I'm going to draw us just to, there's no reason that I have to say we reach 0 speed at this point. It's just they broke it down. It's nice and easy to draw it that way. This, by the way, is T1. That is when we finally come to a rest out there at x equals capital D. So that's that moment that we are at rest. And this makes sense. We start at V0 and we are decreasing in speed until we come down to a rest for a moment in time. So what will this graph look like on the other side? Well, they already sort of again hinted that we've got to be thinking about the areas here. So that's one hint here. We've got this area in this region here. This is a positive area because it's above the x-axis, and that represents the displacement. We actually know that this area here would equal capital D. So that's the distance we moved out to. So now on this other side of the graph here, what do we make it look like? Well, we already said that the acceleration will be less when we go the other way because the tension's fighting the friction. So our slope's got to be less. But we've got to make it have the same total area there. So I'm going to make it take twice the time to get here and as before. But that also means if I've got twice the time, then I'm going to have half the distance. So I'm only going to get, instead of up here we want 1, 2, 3, 4, 5. Here I'm going to go 1, 2.5. So I'm going to make my triangle here twice as long, but only go half the distance here in that case. So there is my other half there. This would be T2 when we reach the back to the original point of x equals 0. And these two triangles each have their own area. This displacement now would be negative d. And again, these two triangles have the same area because I made this one twice the base, if you want to call it that, but only half the height, so their areas should be the same displacement there.